All right. So as Roland said, I'll talk a little bit about what I do here at Stanford. Let's see if we got AV here. I lead a group called the Environmental Assessment and Optimization Group. We focus on environmental impacts analysis for fossil energy systems, largely focusing on greenhouse gas emissions analysis for fossil energy technologies. We pursue sort of a variety of techniques. We use techniques called life cycle assessment, which I'll talk a little bit about today, and also engineering optimization to try and basically minimize the environmental impacts of the energy systems that we use. Most of this work focuses on hydrocarbons, oil and gas, especially unconventional sources of oil, such as the oil sands in Canada, oil shale. Been doing a lot of work on natural gas, which I'll talk about. Let's see here. Just a little bit of sort of preview for what I'm going to talk about today. What I'm going to talk about is not something that's been published yet. Actually, you guys are the first people to see me give a presentation on this. We just submitted this yesterday, right before I came to talk in the panel discussion. I can't, for that reason, because it's under review, I can't actually give you results. I can just sort of give you teasers and interesting things we dug up as part of the research. But I find that actually I much prefer to talk about things I'm doing right now than something I did, 18 months ago, which has already been published. It's a lot more fun for me. So you guys will get sort of the view from the ground about natural gas leakage, which is sort of what I talked about yesterday. Let's see if this works. This does work. Okay. So a few points about natural gas leakage, the general outline. First, I'll talk about why we might care about leakage from natural gas systems. I'll talk about what we think we might know, and by that I mean what is generally understood to be the case about methane leakage. I'll talk about why we might be wrong about what we think we know. And then I'll talk about what we might do to improve our knowledge. And again, this is literally, well, it's not even hot off the presses. It's hopefully soon to be hot off the presses. So why should we care about natural gas leakage? Natural gas is a large fraction of our primary energy supply. This is a 30-plus year time series of yearly fuel shares for U.S. primary energy. So this is basically the fundamental energy sources we consume to power things like electricity generation, our homes, businesses, industry. You can see that natural gas has a fairly stable share, increasing over the last few years, even more so in 2012 and 2013 due to shale gas development. Something like 26% of U.S. primary energy and about 20% of global energy supply. This is likely to increase, not decrease over time. In terms of combustion, natural gas has about half the CO2 intensity of coal per unit of, let's say, electricity produced. It can be even better if you have a really nice, new, modern, efficient coal-fired or natural gas power plant, especially compared to the older power plants we have in the U.S. Unfortunately, not unfortunately, factually, natural gas is 90% methane, which is something, on a mass basis, something like 25 to 33 times more potent than CO2 as a greenhouse gas. This is actually a new number that the IPCC is likely to adopt this fall. On a molar basis, that amounts to something like a factor of 8 to 10. So if you have a mole of carbon, if you oxidize it, or if you don't oxidize it, a mole of carbon in the form of CH4, if you don't oxidize it, something like a factor of 8 to 10 more potent on a 100-year assessment time frame. So obviously, small amounts of leakage because of this potency can actually be pretty important and actually determinative for some of the choices we might make for using natural gas versus coal for various energy sources. Here's a first view of the flows in the U.S. natural gas system. So this is, we're starting off, what do we think we know? Here are all the flows in the natural gas system. Obviously, you guys can't read this, but just to give you the general scheme here, we've got gas wells and oil wells here that produce gas. Some fraction of this is processed. You can process gas to remove basically higher alkanes, C2, C3, ethane, propane, things like this that are more valuable. You then transmit the processed gas. You might store some of it, distribute it in gas lines around your homes and businesses, and then consume it. The relevant factors here, because you can't read the numbers, India's consumption in the U.S., and again, this actually is a U.S.-focused study, is something like 22 trillion cubic feet. These are factors from 2011. And our best estimate, this is the EPA estimate for leakage, is something like 0.4 trillion cubic feet was leaked, or about 1.8% of our consumption, or about 7 teragrams of CH4. So this number is something to keep in mind, 1.8% of consumption. That's sort of the official EPA estimate. They generate this estimate every year of how much gas is leaking. This is the largest source of methane to the atmosphere from anthropogenic sources, actually from all sources of interest in the U.S., followed fairly closely by things like petroleum systems, wastewater treatment, cows, and things like this. But 7 teragrams is the largest source. So what do we think we know? Where might this come from? A source that's been of real interest recently is hydraulic fracturing. And you guys have presumably heard about this, or you're going to hear about this over the course of the week. Hydraulic fracturing, and Roland just actually talked about this in terms of EGS. Hydraulic fracturing involves injecting fracturing fluid under high pressure, which is basically water with some additives, fracturing the rock. And then there's a period called flowback where, especially in a gas well, you want to start producing gas. You release the pressure on the wellbore. You release basically the back pressure. Fluid shoots out of the wellbore and is collected in most cases, the fluid or the liquid portion of it at least, in holding ponds here. That also results in the fairly significant flow of gas because basically the gas pressure is forcing the fluid out. There's a lot of argument about what these factors are. Current active debate, the EPA estimate is something like 0.8 teragrams, or about 10% of natural gas emissions. Because remember, we said on the last slide, we're at about 7 teragrams total. So EPA says maybe 10% is from flowback. There's other things that are sort of more mundane and less sort of newsworthy than fracturing emissions. For example, this is a large gas compressor, or actually it's a moderate-sized gas compressor. They get bigger than this. These emit something like 1.3 teragrams, or approaching 20% of our 7 teragram total. The relevant thing here with leakage is that there's a couple things going on. One of which is that these are sort of human-engineered processes, so they're not imperfect. For example, or they're not perfect; they are imperfect. If you have a reciprocating compressor, for example, there can be gas slippage. You have pistons that are compressing the gas, and of course, no piston fits perfectly, and so you have slippage around the piston, and then this is vented. These sorts of things, right? And so we engineer systems, we try to make them as good as possible, but when you're working with high-pressure gas, there tends to be some leakage. What do we think we know about the impacts of leakage on our choices for using natural gas? These are some interesting plots that it's worth taking some time to unpack. This was published by a guy named Ramon Alvarez in the Proceedings of the National Academies last year. These are on the x-axis. For every case, we have the years until net climate benefit is achieved from switching from a particular fuel to natural gas. And on the y-axis, we have the percent of natural gas leaked. Okay? So as the percentage of, and this, we're going to sort of unpack this example here for the gasoline car. So this is substitution of gasoline, or of natural gas for gasoline. So for example, buying a CNG vehicle. Let's see here, hopefully that. Okay. No. Update for Adobe Reader. Thank you, Adobe. Okay, so where was I? Okay, so this is a gasoline car example. So we're going to say I'm going to sort of trade in my Honda Civic and get a Honda Civic CNG version, which you can purchase. We have instantaneous benefits, since this is the years until net climate benefit achieved. We have instantaneous benefits, that is benefits right away, if leakage is below 1.5%. And we have benefits on a 100-year basis, a 100-year climate impact basis, if our leakage is below something like 3%. You might say, well, why are these different? Why does it matter whether we're assessing our impacts now versus 100 years in the future? Methane has interesting properties, one of which I mentioned already is that it has a higher potency, a higher global warming potential in terms of per kilogram emitted. It traps more heat, but also it has a shorter lifetime, and so this effect actually decays over time. It basically decays to CO2 and asymptotically approaches the CO2 potency over time. And you can see here for a coal-fired power plant, you're at something like 3% for instantaneous benefits and about 7.5% on a 100-year basis. By far the most common assessment period that people use is 100 years. It's not that that's necessarily the only one to use. It's just people think of climate change as sort of a century scale kind of problem. Some people use 20 years, some people use even longer, but the 100 years is very typical. So given from those figures, what do we think we know? We think we know that coal versus gas is very good. We said the cutoff at a 100-year basis was something like 7.5%. EPA says we're at 1.8%. Okay, we're good. A gasoline car switching to natural gas is probably good, but a diesel truck conversion probably has no benefit or maybe is actively bad. That's because diesels are actually very efficient, and so they tend to be hard to beat with natural gas conversion. Okay, so that's what we think we might know. The EPA inventory was completed, and actually I think I started talking about this, but I don't think I finished it. This project, I was tapped to lead a team of about 15 scientists to review the state of the knowledge, basically the last 20 years of knowledge on natural gas leakage, and come up with a summary of sort of where we are. So some of this will be sort of what do we know from the literature, because I can't really talk about the results yet, but I'll give you sort of what we found from the literature. The EPA estimates that I showed you, 1.8%, are largely based on methodologies that were developed in the early 1990s. Since then, there's been a number of studies. This is a study this is an early study in 2003 of these sort of new crop of studies where they looked at methane concentrations, and they found a large plume over Texas, Oklahoma, and Kansas. Their estimated leakage was something over 2 times the EPA leakage for this region. So this was an early study. I'll just sort of run through these. This is a really interesting one. This was literally published maybe 2 weeks ago. This is a study from NOAA, the National Oceanic and Atmospheric Administration. This is in the Uinta Basin in eastern Utah. It's a beautiful place. I like the high desert. It's quite nice. These are oil wells, these blue dots. These are gas wells. These are black dots. This is the flight path flown. Woo, this would be very fun. I've never flown on one of these flights. I'd like to. This is a couple of vertical transects they do. You like to transect basically the profile of the atmosphere to see what's going on vertically as well as horizontally. This is the sort of mass averaged wind direction over the 3-hour flight period in red. And you can see downwind of the gas fields. You see elevated CH4 concentrations in parts per billion here. You can do basically some fancy mathematics, integrate basically the delta between upwind and downwind concentrations, and you always have the wind speed measurements going on. And they estimate leakage of something like 6.2 to 11.7%. This is the second study out of NOAA in the last year that's found high leakage rates. Notably, not really high leakage from the oil wells, although they didn't really do a downwind transect of the oil wells, but over the oil wells is not not a big source there. Here's a recent study. Again, this was late 2012. This is Los Angeles. They took a bunch of samples. They were flying the airplane around, and each of these dots is a sample they took. The color corresponds basically to natural gas concentration. These are guys from Caltech and JPL. They estimate leakage of something like 2.5 to 6%. This actually is even more problematic because downstream sources, that is our homes and businesses, were long thought to not really be major sources. This is not a big gas-producing region. It's a reasonable size oil-producing region, but it's not really a big gas-producing region. And so if this is the leakage rate, then that means that our homes are perhaps much leakier than we thought. This is a fun one. This is a study from 2012. I like to show this and sort of to make fun of you guys in the plight you're about to enter because you're entering graduate school. They say in the paper, we drove 785 miles of roads in Boston. We, meaning a first or second year graduate student. I've been to Boston a number of times. I would not want to drive 785 miles of roads in Boston. With a methane sniffer on the car. This is developed by a local company called Picaro. They're actually in the South Bay. They have a very sensitive isotopic gas analyzer. They can detect not just methane concentration, but also the isotopic composition of the methane, so you can tell if it's basically a fossil source or a biogenic source. These are all the spikes, something like 3,350 spikes, And they here use Google Earth to plot some really high ones. These are ppm, not ppb. That's very bad. The last slide had ppm or ppb. So basically, I can't really give you guys the conclusions, but basically multiple studies from air basin to sort of national scale suggested that EPA might be underestimating the leakage, and there's fairly good evidence for that. At this point, we reviewed about 200 studies, and there's about 15 or 20 of them that present really good evidence. So that's sort of the summary. I can't give much more detail than that. Very exciting. So I can talk about what we might do to improve our knowledge. From sort of the device level, there's kind of two levels at which people study leakage. They just study leakage sort of at devices, and they study leakage from the air, and these are sort of called top-down and bottom-up. Here's a guy sampling what's called a rod packing vent, which is a vent on basically the packing that's around the cylinder shaft in a reciprocating compressor. To prevent gas leakage. There's a vent there because some gas is always going to slip by, so he's sampling it here with the device. Interestingly, so this is from this University of Texas study that was funded by EPA. There's really interesting things going on. These are a bunch of categories, blow-down lines, valves, flanges. You norm them by their mean, and then you plot basically the number of samples seen as a function of the mean, and you can see here that this is a very skewed distribution. We have some that are way out here at 25 times the mean, etc. So this doesn't really look like a normal distribution. This looks like a skewed distribution. So basically from the bottom up, we see that emission sources appear to be very heterogeneous. Sometimes in statistics this is called heavy-tailed or fat-tailed. There's a lot more high emitters than we think there might be. And we really need better estimates needed of this extreme behavior. The most interesting, I'll diverge here for just a second, and I've got one more slide and then questions. The most interesting study done since the original EPA studies of the early 1990s was a study where they went around and sampled about 75,000 sources at like 5 or 6 gas plants. So again, this is not necessarily the funnest job. You're going around and sampling 75,000 sources. About 1,600 of them are leaking. Of this 1,600, the top 10 accounted for 60% of the total gas leaked. The top 10 out of 75,000 sources corresponded to 60%, so that's 0.015% of your sources corresponded to 60% of your total volume leakage. This is a needle in a haystack problem of ultimate dimensions. And so if you go around and take small samples from this and say, what's my average leak rate from a compressor? If you don't find that one, on the other side of town that just happens to be belching methane because someone left a flap open or didn't tighten something down or whatever the case may be, you may not have a representative sample. So this makes actually statistically understanding what's going on very challenging. We need more studies at the atmospheric scale. Here's a similar atmospheric trace over the LA basin from a 2013 study. Like I said, there are actively airplanes flying around, probably not as we speak, but there are many studies going on right now. This is a very sort of hot topic. We need better atmospheric measurements with improved geographic and temporal coverage. That Utah study was like a couple days. Well, they had like 12 days of flights, but only a couple days were usable, right? So this is not over the course of the year. Flight time is very expensive, so we need a lot more data. I think we need smaller scale, but still sort of atmospheric studies, so things like drones, and so you could have them sort of fly patterns cheaply and get lots of data over time. And then we need to improve sampling of multiple species simultaneously. They're all starting to do this, but in the past there was less of this, where we're sampling things like ethane and propane to be able to distinguish cows and other sort of biogenic sources from natural gas sources. Okay, so really quick, natural gas leakage could be significantly higher. It's still unclear how much of the atmospheric excess is due to natural gas sources. It's still unclear what sources within the natural gas sector are responsible. Lots of work to be done. And so this is very exciting and very interesting, and hopefully we'll fix the problem. So anyway, I've got, I think, 5 or 10 minutes for questions. I'm sorry if I went too fast. I know it's the end of the day. It's at least cooler in here than it was yesterday. I was on the verge of tipping over in my seat in case any of you noticed. It's pretty bad. Yeah.
So in case you're right, and the EPA is underestimating significantly this leakage problem, is natural gas making climate worse?
So that goes back to, good question. It all depends. All these questions are always comparative. It's always worse compared to what else would we do to generate our energy. Uinta Basin, they found sort of 6 to 11%. It's almost certain there's a variety of evidence at very large, like continental scales, like flying airplanes all the way across the country, that suggests that that just can't be typical. If that was typical, we'd see way more methane in the atmosphere. So you can really constrain it almost from the sort of continental scale concentrations. There's no way, it's very unlikely, I don't want to say there's no way, it's very improbable that we're at these sort of levels, 7 and 8% on average. That's probably a very atypical case. So coal to gas switching is almost certainly a good deal. Heavy duty vehicles, not likely, and gasoline cars are sort of up in the air, is the short version. Yeah.
So you mentioned that most of the gas leakage comes from like a few small sources. This might be an ignorant question, but wouldn't the mercaptan that we add to the natural gas be something that people would notice almost immediately if that were that large of a concentration coming from a small area?
Well, I mean, it depends on when that happens. For one thing, that's usually added later on in the so that doesn't happen at the well site. And so, well site and then upstream processing, sort of the initial part of the processing, that it hasn't been added yet. It's added in the sort of the back end of the processing stage. People do use that. One, I'll call it low tech, but apparently effective method that I've heard people say that work at gas companies. You can actually, the vultures will hone in on the mercaptans. They have very, PPB sort of sensors in their nose. Thank you, evolution. So vultures will actually circle over lines and high pressure gas lines. This is just something that somebody told me sort of over lunch. So, yes, so this can be a source. Sort of a way to find things. Unfortunately, it's not necessarily foolproof. So the Wenberg study, which was a study from Los Angeles, they estimate sort of 2 to 5% leakage, mostly from downstream sort of homes and businesses. They actually make an estimate that at those sorts of rates, if it was a slow, constant leak, and you had a certain sort of volume of building and number of air changes per hour and things like this, it would actually be, the odorant concentration would be a couple orders of magnitude below what we could smell. And so if you have a sort of short-term, potent, high-volume leak in a home or business, you're certainly going to smell it. If you have just a few sort of here and there that are leaking a couple % of your total gas consumption, then they speculate that perhaps you might not smell it. Road sniffers, so PG&E, especially in the Bay Area, they're driving all around with sniffer trucks. They were driving by my house the other day, a couple months ago. They wouldn't see it either, right? It would be, especially once you get away from a house where the concentration is elevated by a small amount, you likely wouldn't see it with a sniffer. So it could be very, and that's actually the hardest, that's a bad case. If that's the case, that it's all these diffuse little sort of sources, that's actually a much harder problem to solve than sort of, I left the flange unscrewed or something like this. Which you can go around with a sniffer and find it, or you can smell it.
What's kind of the oversight right now that is required to go around with a methane sniffer on your sites and look for leaks, or?
There are recommended practices. There's a variety of companies that that participate. These are typically called directed inspection and maintenance procedures. Is sort of the official terminology for them. It's not clear that they're as actively practiced as they should be. Yeah, and there's a variety of, there's actually the regulatory environment is not something I pay a great amount of attention to. I'm more on the technical side. So, but my impression is that landscape is changing very rapidly, but a lot of it is focused more on technology adoption rather than enforcement of monitoring. But that's actually something I don't have the specifics on in my head.
I'm just wondering about fracking and what those rates might look like in comparison to what you've looked at here.
Yeah, so that's something we looked at because we actually created a couple estimates for fracking. I can't give you the numbers. It doesn't appear that fracking is actually the story for a variety of reasons that I could talk about. I'm getting the sort of hook over here, so get off the stage. Yeah, it doesn't actually look like fracking is necessarily the story. It could be a contributor, but it's more likely a minor contributor just compared to just the larger system. The actual fracking process is only one part of the system. There's processing, compression, and transmission, and end use. And so actually it doesn't look like that's the story. It may be part of the story. Maybe one more, since I'm getting the hook here, if there is one more. Yes, I know you. Hi.
Do you have a sense for how much of that 7 teragrams is from pipe clearances on the transmission system?
The EPA estimate, I don't actually. I should have that number off the top of my head. The EPA estimate for transmission, I don't know what it is. They're split. Do I have it somewhere on here? Transmission, there I do have it. 0.117 out of 0.4, so maybe a quarter of it is from transmission, and I'm not sure exactly. A lot of that is from.
Mostly intentional.
I think a lot of that is from compression. That's a big source. Our transmission grade compressors are a large source. I should know that though. This is good. This was a good dry run. You guys asked me questions that I didn't know the answer to. So. Okay, thanks everyone.